Welcome back to another episode of Scientifically Simple. I just want to thank you for joining us today. So we are going to be talking about hydrogen synthesis technology because clearly we didn't have enough very complex topics to cover. That's sarcasm, of course. Mr. Fowd has actually spent a lot of time studying hydrogen, obviously as it relates to ammonia and other processes. So we're going to be delving kind of into the specifics of hydrogen, especially as it's taken on a new focus here recently as far as like green technology goes, and as you know, governments and organizations look for alternatives to like methane and things of that nature. Take it away, Mr. Fowd.
Thanks, Brandon. And you can always call me Mo. I'm fine with that.
Mr. Fowd.
So, yep. Can you hear me?
Yeah, you're good.
Oh, okay. I thought you lost me or something. Okay, so our episode today is to talk about hydrogen synthesis and the how important the hydrogen molecule in general for so many applications, whether it's gonna be used in refineries, in hydrotreating, in fertilizers, in production of critical chemicals like ammonia and methanol, and even rocket fuel. And of course, its importance is becoming more and more critical nowadays as we go more into the blue technologies and green technologies, where we are trying to find alternative that can fill the gap for the same energy density of crude oil and gasoline, etc., by something was almost as close to that energy density. So hydrogen, of course, is going to be futuristic wise, will be used in so many things, like potentially whether it's as a hydrogen itself or being part of a molecule like ammonia, for example, being used as a fuel, or if we progress a little bit into the future, hopefully one day we can be utilizing the same engine of the sun, which is the hydrogen fusion, which is the ultimate ultimate energy density by all means. This is something that's seriously sustainable for a very long time, because it's literally turning mass into energy, and we know from Einstein's mass energy equivalency how big of a deal is that. And not to mention turning hydrogen into helium, it doesn't produce any carbon footprint in the first place. So Brandon and I, we wanted to be having a very nice subcategory for the hydrogen synthesis technologies, and we are planning to be having at least 4 different episodes around that. The first one, which is the current one, what we're gonna be going through, is intro to hydrogen technology in general. That will be including technologies that are still in infant phase, like on a pilot or a lab development phase, or even ideation phase, and what has been established in industry to produce hydrogen. And that will be the second part of that episode, talking about the industrial applications. So for a start, hydrogen synthesis technologies, as you can see there, can be segregated based on 2 main categories. Either it's based on carbon technology or water-based technology. Water-based technology is straightforward. You have water, and we're splitting it one way or another into hydrogen and oxygen, which is the main overall process for that. Falls under the umbrella of electrolysis. Now, the carbon-based technology, that pretty much anything, pretty much the organic chemistry, anything that has carbon and hydrogen, and I have a way of extracting the hydrogen from that hydrocarbon backbone. That hydrocarbon backbone doesn't have to be just hydrogen and carbon. It can be, it can be aldehyde, it can be amino acid, it can be anything. 100%. But technically, if it's an organic chemical and it has a carbon in its backbone, that's pretty much what the carbon-based technology is. And of course,
and it's good.
That
Oh, sorry to
yeah.
interrupt. It's good to note that based on a previous discussion we had, one of the side products of the propane dehydrogenation process is actually hydrogen gas.
Yeah,
Tying that full
absolutely.
circle. Right.
Yep. But the part there that it doesn't get like its own how I can say that, like that technology has never been looked at as a precious hydrogen plant, because the main outcome of that technology is to make propylene, and propylene pretty much was the main product, and hydrogen
Right.
was just like being used, you
Right.
know. But yeah, you're right. Any process, you know, like
Right.
even like in refineries, you probably can find from the cracking technology, you probably will get hydrogen, but nobody even pay attention to those. But it's actually a very very precious, you know, it's a very precious product. Like
Right.
you would be surprised, like how it just depends on the school. Like if you are coming from a fertilizer background, you know how well
Yeah.
you know well how precious hydrogen is. If you
That's
are
funny to
in,
think about it like that. Yeah.
yeah, if you are coming from background in methanol or a school of thought for, you know, recently with green technologies, you will know how hydrogen is precious. So other industries, like whether it's in refineries or petrochemicals, like, you know, propane dehydrogenation as an example, it doesn't get the same appreciation, because again it's a side product. It's just like an afterthought pretty much.
Weird.
Yeah, it's yeah, which is, yeah, it's crazy. So the carbon-based technology can be biological, and everybody is is aware of that. There is a lot of biological processes that literally makes hydrogen. I mean, that's actually like part of the photosynthesis process. And there is actually like something like there is an enzyme in plants, like and even like something like cyanobacteria that has an enzyme called hydrogenase to literally make hydrogen out of your carbohydrates or starch. So biologically, there is a well-established mechanism in biological life to make hydrogen. That hydrogen is going to be used in so many other things intermediary. Like, it's not making hydrogen just as an end product. It's going to be used as part of the metabolism itself. Now, there is of course the fossil fuel based kind of technologies, which is the dominant, given how economically feasible and how much the fossil fuels are by definition very rich in hydrogen, in terms of like the hydrogen density per in that backbone of that molecule. So, you look at methane or ethane, for example, there's 4 hydrogen atoms in the middle of 5 atoms. So that's, the most dense kind of like molecule in terms of like hydrogen per mole of molecule. So that will be like the steam reforming, autothermal reforming, partial oxidation. Those 3 are pretty much one and the same. It's just like it's a different way of how and what is being introduced with methane. But at the end of the day, all of them, they are gonna make steam one way or another. And the main feedstock is gonna be mainly natural gas. There is of course other type of feedstocks, but they are less known. But basically, steam, autothermal reforming, along with partial oxidation, those are gonna be based on natural gas going into hydrogen. Gasification is based mainly on coal, and that tend to be like very popular in East Asia because of abundance of coal, for example.
Right. Yeah.
And along with pyrolysis, it's the same idea. It's just different reaction conditions. But like mainly, this coal is not as abundant. How can I say this? It's not as feasible hydrogen manufacturer as methane, because in gasification, you have coal reacts with steam to make carbon monoxide and hydrogen. So the hydrogen is coming from steam. The coke is not providing anything. beyond, like in terms of hydrogen value. However, in methane, you have 2 moles of water reacting with 1 mole of methane to give you 4 moles of hydrogen. So it's just simple as that. You have natural gas coming from the ground, coal coming from a mining, which is also from the ground. Just from the ground state, if you have natural gas, you are well ahead in terms of hydrogen production versus the coal gasification, for example. So those pretty much the different methods that we're gonna briefly address in this episode. So as we mentioned, anything that's based on water, that's pretty much electrolysis technologies, and there's like 3 types of technologies that's super similar. All of them are, it's gonna be like based on galvanic cell or electrolytic cell, based on if I am making current or I'm inducing current, like fuel cells versus corrosion, for example. So those can be like 3 different processes. There is solid oxides, there is the proton exchange membrane, which is the middle one, is B, and there is the diaphragm based. They differ in the beside like having the anode, cathode, and the electrolyte, there is another things that can be introduced into that process, and there is the temperatures difference. So solid oxides, these are like solid ions, and pretty much they can handle high temperatures, and the higher the temperatures, the higher the reaction rates, and that's why like those can be feasible in some applications. If you want hydrogen generations that happens at a very high rates, solid oxides can be a potential proposal for that. The PEM or the proton exchange membranes are very famous because they tend to be like having a membrane between the anode and cathode, and that membrane has to be definitely not conductive, because at the end of the day you don't want to mix the electrolyte on the anode side with the cathode side. Otherwise the whole thing is going to be a mess. So the good thing about the PEM is that the hydrogen comes from one direction, gets splits into electron and the proton, which is the hydrogen itself. That proton would migrate into the other side where it will meet the oxygen and it get oxidized and turn into water. The electron that basically leaves the hydrogen behind, it actually goes into the circuit, and pretty much that's what you get, like the flow of electrons in a circuit. That's how electricity is made. And in doing so, the electron, along with the oxygen meeting with the hydrogen, protons, they make the water, and that's pretty much what you have there. So that split happens at the anode side. Hydrogen in a gas phase basically gets absorbed on the anode and gets splits into electrons and protons in the liquid phase. The migration of protons go from the anode to the cathode, because at the end of the day the proton is a positively charged, it want to go away from the anode. The electrons cannot go in that direction because there is a membrane, and that membrane is not conductive, and that's why the electrons would go in that direction. It's going to the least resistance, and that's how you create the circuit itself. The same applies.
That is really cool.
Yep, it's very interesting technology, and it's one of the popular ones. If you look into like the hydrogen fuel cells, but still again it has a lot of challenges. Some of them is like that you want to make sure that the water that's being formed, you need it to be in vapor phase, not in liquid phase, because if water in liquid phase, it causes all type of issues, including corrosion and impurities and stuff like that. Like one of the examples, some fuel cells, like when they were created in the lab, of course you're creating this in a perfect environment, but like once you try to be going to a pilot version,
Yeah.
the water
Yeah.
was contaminated the water had a contamination of silica, and silica pretty much destroyed the catalytic system of this fuel cell. So you can imagine, like, you know, there is the perfect setup that we have in our labs in general, and this is like one of the things that we are going to be highlighting as we go through all of this. You have a perfect environment in the lab. What you have in your mind, you are literally creating in the lab. When you go out there in real life, real life doesn't exactly, wouldn't be always be what you have perfected in the lab. Water 100%. Is going to be having some contamination. The anode and the cathode might not be as perfectly as you have bought from that lab vendor. It might not as pure. So your anode impurities can be playing a factor in this. The cathode purification, purity, the electrolyte that you're getting, the water. So all these things will start to be showing up in the pilot, and that's the whole purpose of having a pilot phase between the commercial and the lab, because all these things will show up in the pilot phase.
100%. Yep.
So that pretty much this is for the electrolysis in a pure sense. You have anode, you have a cathode, you have you have water that's being split into, you have hydrogen gas splitting into protons, electrons, meeting oxygen on the other end, making water, and in the process producing electrons. Any electrons in a flow, that's pretty much a current, and that's how you make electricity. The second phase of that, like the second generation of that, is something called Photonic Technology. That can be either
really
like
cool, because I had never even heard of this.
Yeah, so that's actually like in a very infant. That's why it's really an infant phase at this point. Both of them are using photons as a driving force. But the difference between the photoelectrolysis and photocatalytic technology, the photocatalytic is actually adding a catalyst, so it reduces the activation energy. So pretty much it works around of speeding up how the hydrogen is being evolved per unit cell. The other one was the photoelectrolysis. You would imagine it's a little bit primitive, or it can be your typical standard way of making hydrogen. So you can actually like be talking about this presentation and basically say, hey, I have a platinum, and platinum is it works as a electrode in this case, but also it can be acting as a catalyst, because hydrogen on a platinum that has always been like the bread and butter in any catalysis that deal with hydrogen and platinum.
Yeah, true.
But like basically that's the typical setup between both of them. The photocatalytic does not need to be based on your typical galvanic cell or electrocatalytic cell. As you see, you have a catalyst and you have water immersed in water, and you are using photons with a given frequency, which is basically an energy carrier, to split the water into hydrogen and oxygen. In that sense, you're not making electricity. Now you are making what? You are making hydrogen as a product. Now the hydrogen can be used for anything else. The main concern with that technology, unfortunately, is the intensity. Because at the end of the day, your rate of hydrogen generation is going to be, how can I say that, surface area, like limitation. Because how much you can focus that light. So that's going to be literally the metric for the economic feasibility of the system. Because you can imagine if you the whatever area you're being exposed to, the geometry is going to be the limitation. So if you want to make it like a hydrogen, now you can imagine the volume of that system itself, how big it's gonna be. Because it's no longer the catalyst itself. It's literally one of your reactant, which is the energy source. Your photons are going to be like the limited supply. So that's for for the electrolysis based technology.
Is there
Moving
any,
to
yeah, the photonic technology, is there any of that being commercialized right now, or is it still kind of lab phase?
From what I've seen, I didn't see anything that goes beyond small pilot scale. Like,
I was curious if anybody had like hundreds of millions of dollars in funding for this.
I wouldn't be surprised if
I mean,
there
it's
will
cool,
be. I mean, like,
but
nowadays,
to your point, the size
Mm-hmm.
that you would need to have something that was, you know,
Mm-hmm.
effectively
And then you're
industrial
gonna
scale, it would be massive.
That's true, and also like the problem is, so you have you have the intensity issue, and also on top of that, you have the photon frequency. So where that photon is gonna come from? Is it gonna be a sunlight? So we're talking about like a low energy level, you know, because we're talking about visible light.
Yeah, good point.
Or we are or are we talking about ultraviolet or higher? But like again, whenever you are going into that spectrum, people are gonna be, I mean, like the factor that's gonna be need to be addressed. Okay, now I have a photon source of high quality. What's gonna be, where is that gonna come from? Am I using electricity to make that?
That's a really good point. Yeah, good point.
And then if you are making electricity to make photons to make hydrogen, would I rather do that, or would I just like do the photoelectrolysis instead? I mean, because you know what's going, yeah. So both of them have their pros and cons. I would assume the pros is simplicity for photocatalytic. You are literally have your catalyst in a given photo reactor type. You are generating photons,
right?
And it's pretty much simple, relatively speaking.
It's cool. I just to your point, I wonder how much. I wonder if it could survive in industry. I mean,
there is that, of course. The cons, of course, like, you know, the part that we just addressed, like limitation, the scale, like how big the system is going to be. Is it economically feasible? Where is the source of that energy is going to come from?
Right.
I'm going to be paying.
It sounds cool, but the more you talk about it, it sounds like it would cost a fortune versus what you actually generate from the process. I don't.
Absolutely.
I don't know.
And then you go to the
photo. It doesn't sound feasible.
The photoelectrolysis is trying instead to be like using what's it called? The electrolysis, as you know, but like incorporating the photons into that massive energy level.
Yeah.
You know what I mean?
Right.
It's like trying to. The part that I really don't get around that is like it might actually make it more complicated for not much of a benefit.
Yeah.
Like it's like trying to be having a multi-source of energy.
Yeah.
But it can be actually like somehow counteracting against each other, because like each one of them can have its own variables to improve.
Yeah, I mean it's a super cool technology. I just you get past the lab, I don't really see where you go with it.
Yep.
Especially in light of some of the alternatives.
Electrolysis in general is very, but like even when you go to the electrolysis side, it's very expensive, because beyond just like the fact, you know, you have a nice electrode, anode and cathode, and you just have a nice electrolyte. That unit, that entity is very complex, because these cells, you could have thousands of them, not just one of them in real life. So just imagine if there is any defect whatsoever, trying to trace that is gonna be like, you know, a big challenge.
I wish you luck. Yeah.
And the second part, the reliability and the preventive maintenance, because like we mentioned earlier, that's not a lab anymore. This is a commercial. So the quality of electrolytes that comes in, or electrodes, how are you gonna keep up with the anode corrosion rate? Whenever you're gonna be replacing that, you are talking about like an electric circuit. So the electric
That's excellent
circuits
point.
are by definition super complicated, and there's a lot of challenges that comes with them. So yeah, they like in the media in general, we always look at the battery or a fuel cell as like, you know, it's simple here, like, you know, it's pretty small thing here, but in reality,
agree.
whenever you want an
Yeah.
application, whenever you go to an application, these cells are so small by definition because they need to maximize the surface area per unit volume. So they need to go small.
Right.
They can be
Right.
big. If they go big, they become expensive, like, you know, like the photocatalytic process. So in order for the for electrolysis to work, the cell size need to be minimized to maximize the area per unit volume.
Right.
But the application itself requires a given megawatt.
Right.
So when you divide that megawatt by the output of that small cell, you would imagine how many cells you're gonna have. So that's pretty much how complicated it
yeah,
is.
that's tough. Yeah.
That's like equivalent, for example, that if I would go to a steam reformer that we're gonna be talking about later on,
Yeah.
and instead of like showing you the whole reformer, it's like the equivalent of like, well, I can make hydrogen in one single tube. Yes, you can, but this is just like a sample of that's gonna be like pretty much, you know, extrapolated, like, or multiplied in so many factors. So that's pretty much the electrolysis. Another thing that I just want to be adding when it comes to electrolysis is actually like way older than all the it is the oldest hydrogen process. Electrolysis was the number one thing people used back in the 40s and the 50s to make hydrogen. When natural gas and fossil fuel based hydrogen was not known yet. So the first thing that has been done was using electricity to be splitting water into hydrogen and oxygen, and, you know, that's how hydrogen was made. So here is a challenge. If you look at the energy balance of the hydrogen manufacturing from electrolysis, to make 1 mole of hydrogen from water, it would cost you as much as 4 times the energy that you would need to make the same mole of hydrogen from methane.
Jeez, really?
This is just like a simple thermodynamics. You don't even need to talk about anything. This is just literally that. Just if you take the hydrogen plus oxygen to give you water, or reversible to make it the other way around, you would look at that, how much the heat of enthalpy itself, and compare this to the heat of enthalpy of hydrogen from methane. Just like first law of thermodynamics. Methane wins. You are not even talking about catalysts. You're not talking about like where the energy source is gonna be coming from. You are literally saying which one is a cheaper source. Like natural gas is coming from the ground. Here is your feedstock. There is nothing making the natural gas for me. It's coming from a given initial point. When you go to when you move into the electrolysis part, you have the water, which is available, it's true. But now, irrespective of where is that energy is gonna come from, it will be 4 times the amount that you would need when you need to make it from methane. That's just like a simple.
But what's so funny is like when you hear about like hydrogen generation technologies, a lot of it is electrolysis focused. You don't really hear as much about the other ones, and nobody talks about. And I hate to use this word, but it is inefficient relative to alternatives, and nobody brings that up. I really
think it's mainly when it's addressed that way, it's coming from the fact it's something new, So
Right.
it hasn't been vetted thoroughly. Because, like, whenever something new is happening,
Yeah,
we
I mean,
tend to
fair
be
point.
like,
Fair point.
we tend to be, we tend to encourage it, and we're trying to be like, have a high hopes that it will be a very good alternative. But like, once the ideas start to get vetted, that it will eventually like meet that. Because at the end of the day, the bottom line is going to be why it never worked before, and that's the core.
Oh, yeah.
And that's the core reason why
Yeah.
electrolysis, for example,
Well said.
like, I mean, electrolysis was the number one technology for hydrogen manufacturing, and then it shifted to natural gas.
Yeah.
Now we are trying to get to that without actually addressing what has been improved.
I mean, that is
in
an
that direction.
excellent point. Yeah.
So yeah, so when you address like something like the photocatalytic, for example, yeah, that's a potential idea that you can look into it. But like whenever you're looking into electricity, like in just a pure abstract term, pure electricity, anode, cathode, and water, yes, that has been addressed previously. So that would be like the part that we need to be addressing, and it's definitely not the kinetics part. That's what I can be like telling you, because kinetics is not gonna go around the energy demand of the process. That's
Right.
never gonna happen. Kinetics
Right.
is awesome once we already create that. That's like we have addressed. We're gonna be addressing later as part of the bundle of these episodes. Is like thermodynamics again. It sets the validation for whether the claims that's coming with a given idea has a valid point or not. If it has a valid point, then you move to the kinetics terms, and you move to like, okay, now I need to make this a commercial application where I need to maximize my production, for example. That's where kinetics jumps in. Kinetics is not like some plan B for thermodynamics in this case. So that just that's the part that
Yeah.
because like
Yeah.
you would be surprised. There has been a lot of great papers written about this, but also like you could find a lot of papers that always address the kinetics and how like a given novel catalyst has been found, but still fails to establish or to address that the energy demand of the process is still the same. So that's the part.
100%.
Now,
Yeah.
moving to like now one of my favorite actually parts of hydrogen manufacturing, and I really think like in the future it might be holding a key for intermediate hydrogen production at some point.
Yeah, this
which
is
is the
very
bio-based
cool.
technology. Yeah, absolutely. I mean, it's my favorite topic in hydrogen technology, and it's like daughter products like ammonia or methanol, etc. The reason why it's actually like it's there in nature, it's already well established, and the perfect thing about these type of technologies, it's literally using some sort of heat energy and a bioprocess and a bioorganism to make a high quality product from low quality energy. So, for example, if I would be comparing something like the algae or cyanobacteria hydrogen formation, the building block of that process, the reactor of that process, is a bacteria, and it's actually like using something like a photosynthesis, where it's simple energy coming from heat energy or light energy from the sun, and making something valuable as hydrogen. So you are turning a low value source into a high value product. When you compare this with, for example, with electrolysis, electricity is a high quality source.
I agree.
Electricity is very, like, you can't just like, drill a
Electricity
hole
is
in your
not
back.
free.
Yeah,
Yeah.
you can't drill a hole in your backyard, sorry, and
Yeah.
find electrons flowing out of there. You literally
Yeah.
have to have some type of Rankine cycle or something where you are burning something, producing heat
Right.
to make electricity. So in a sense, there is always entropy tax paid there. You have heat turning into mechanical, mechanical turning into electricity,
Right.
and then you're using this to make hydrogen. So
Right.
it's a nice process, but at the end of the day, if you compare it versus something like a bacteria or bioorganism that's literally taking wastes what we consider waste in nature, along with like abundant energy that doesn't need, precious metals to make solar cells, to turn energy like starch into hydrogen. So that's why I really think biology or bioengineering holds an intermediate key for hydrogen production.
I mean, to your point, I kind of view
yeah.
this as the next frontier. I mean, there
My
are
opinion-
certain chemical materials that we look at as being very difficult to produce for one reason or another. I mean, the fact that bacteria can just produce hydrogen just
Oh yeah,
at will, something that you like, to your point, like electrolysis, methane reforming, all that stuff, the efforts that you have to go through to produce it right now. If it becomes that simple, you just have a bunch of bacteria producing hydrogen gas for you, you just pull it off and you just use it. What else could reproduce in that same manner?
absolutely. Yeah, exactly. That's the beauty of this process. It's and by the way, like something like cyanobacteria, not only they make hydrogen,
Super
they
cool.
they can actually produce ammonia as well. By the way, they have the capability of making ammonia. So that's the cool part about like biological systems. They excel at this type of transformations without the high maintenance requirements to make the same thing. Like you look at something like photosynthesis. You see like how like that's pretty much like the core of life, and that's how biology works in every way. Versus solar cell, you need to be like mining metals of a given purity.
Excellent point.
So all the way to turn heat into electricity. And on top of this, in the middle of doing that process, the solar cell itself, efficiency over 25 years, it's just like, has exponential decay.
Right.
So that's why like I really think like biology has fascinating processes. That's what I can say. Has a very fascinating processes that are to be tapped into. The challenge about these type of processes, it becomes like a core chemical engineering
Agreed.
challenge, because
Agreed.
it's literally the process exists. It's all about like how I can make that process economically feasible.
100%.
And that's the key there. Now, I will move like to the traditional fossil fuel based hydrogen manufacturing. So gasification and pyrolysis relatively are newer than the steam methane reforming, and they are abundant, as I mentioned, in countries where coal is available. Like they don't have enough amount of crude oil or natural gas, or they have to import it from somewhere else. So biomass in general can be utilized to make hydrogen and a mix of some other molecules called syngas. Syngas is anything It's a short for synthesis gas. So if I have carbon monoxide and hydrogen to make methanol, carbon monoxide and hydrogen is called synthesis gas. If you are in ammonia, your synthesis gas is hydrogen and nitrogen. So it's pretty much like the ingredients for making your end product. And it's, if you say syngas, it's gonna be hydrogen with something. So that's just like to clarify that point. If people see syngas so many times, anything syngas, it has hydrogen, but what's gonna be with that hydrogen is going to be like telling what process you are making. If you have nitrogen, it's gonna be ammonia. If you have carbon dioxide and carbon monoxide mixture, you're gonna make methanol. So coal gasification, as we mentioned, differs from pyrolysis in the conditions. So gasification utilizes the air and steam to have some type of partial oxidation and steaming of the coke to make the syngas. Pyrolysis, it just simmers the coke itself, and you would be like saying, like, how you're gonna even make hydrogen from coke? Well, you're gonna need to go to the biomass itself, and that's when you go to the solid kind of composition, depending on the coal that you have, there is moisture in it. So you don't need to be introducing the steam if the coal has a lot of moisture in it. You can just heat it up, and the moisture within is going to be reactant with coal. So that's why, like, the pyrolysis, you see it up there, is one of the is one potential. But of course, like, in terms of quality, the more water quality, the more water composition in that coal, the lower quality it is, because not everybody uses coal for making hydrogen. If it's used as an energy source, the calorific value of that coal is going to be low, and hence its price is low. So the hydrogen dudes loves that type to make pyrolysis, because it can, in some places where the water supply is not available, and if you don't want to deal with the water treatment hassle for your process itself,
that is really clever.
Yes, exactly. The water is coming from within the feedstock itself. So that's a really nice thing about the pyrolysis. But again, it's energy intensive. All of them are energy intensive. And of course, you're gonna have to find a way to deal with the heavy compounds that come out of the coal, which is the char, the tar, all these things. And of course, there's gonna be a lot of environmental constraints and expense associated with capturing all these ashes and stuff that's coming out of this process. So that's pretty much like an overview of how the gasification and pyrolysis looks like. Now, like, moving to almost like the process that I grew up in chemical engineering in general. And
I was gonna say, do you want to give it a big hug real quick?
That's pretty much, the reformer. Every time every time I see a reformer, I just want to give it a hug. Anywhere I go, whatever plant I go to or work with, I always, like, the reformer. By the way, one of the best chemical engineering equipment that has been done in terms of, if you are a chemical engineer, there is no one single phenomena that you have studied in chemical engineering that you would not find in this system. So if we are talking about heat transfer, you have radiation, you have convection, and you have conduction happening in one equipment. Here is your heat transfer. If you are talking about mass transport, heterogeneous catalysis, this is your reactions happening on a solid catalyst is inside those tubes. So here is your chemical reaction, mass transfer, entangled with heat transfer. So, and on top of this, you're talking about, like, the heat temperatures and the temperature levels you're dealing with, the pressures, the fact that you have a high partial pressure of hydrogen, and as we would address later on in the piping slides that we're going to talk about separately, hydrogen requires a given alloys. Otherwise, it can actually, like, you know, go through the pores of the alloy. Hydrogen is too small.
Oh yeah.
So like the middle crystal lattice, it's like pretty much like, you know, going through doors for hydrogen.
Dude, I had
like,
no clue till I started working in stainless. My manager told me that was a real thing. Like, if hydrogen gets inside the steel, it'll ruin it. They call it hydrogen embrittlement.
100%.
Just straight up ruin it.
That's literally that.
That's insane.
And pretty much all it does do, you have gas going through, like, you know, the fabric of your metal.
That's crazy.
It's creating deficiencies. So
That's
the metal
crazy.
itself start lose strength, like all type of material strength, because of that. And that's why, like, you have a specialty alloys that goes into those tubes, either to mainly to delay the onset of that. These tubes actually tend to be like, you tend to take them out and actually get new ones every 20 years or so. So even like the specialty alloys, they are not, you know, 100% resistant. They just like try to hold it together for a longer time. That's pretty much what it is. Yeah, hydrogen is a brutal molecule.
Crazy,
despite how small
man.
it is. Yeah, I know. So that's like the steam reformer is the core of the steam methane reforming. And that's pretty much the process that uses natural gas. It's the most famous established process for hydrogen manufacturing on a mass scale worldwide. Everywhere you go, whether it's a hydrogen, whether it's methanol, whether it's ammonia, this is the process, because it requires low energy level, and not low energy in terms of the demand. It requires heat energy, doesn't require electricity. It uses methane, which it has the highest hydrogen density per mole of any molecule that, you know, manufacturally available. And more importantly, the abundance of natural gas. So, but yeah, this is pretty much like the established process. I'm sorry that I have like everything there in Celsius and bar. I have been going back and forth between English units and metric units. I lost my brain. Like, till now, like, if you would ask me about anything in the ammonia plant, for example, anything that comes to my mind, I need to convert it to Celsius to see if it's true or not. Like, like, you have to pick a system as a reference. You can't wiggle between them. I mean, at some point you will know. For example, the 780 Celsius or 790 Celsius exit of the reformer is like equivalent to, I don't know, 1400 Fahrenheit or something. So there are things that gets time there. But yeah, the pressure is a big problem. Always PSI and bar all this time. But that's pretty much for the intro to the hydrogen synthesis technologies based on water and carbon methods. And with, you know, our next episode is going to be like about like the steam methane reforming. We definitely kept it last, but it's not the least important. It's definitely one of the most critical important processes out there, especially in the chemical industry. And that's where we are going to be addressing in details the different the process flow diagram of a typical process, and what type of chemical reactors that we have there in that train to be making hydrogen from natural gas.
All right. Dang, that was a lot of material. That was really well done. Thank you, Mo. So I really do hope you enjoyed this video. You can find us on YouTube at Scientifically Simple, or check out the podcast, Scientifically Simple. We've got audio, we've got video, we've got everything you need. You want to send us an email, send one to sciencemadesimple@outlook.com. There will be some details in the show notes below. And as always, thank you for your time.